Welcome to AP Bio, and today we're continuing metabolism.
Listen, man, you were late. You're late. All right.
Never felt.
I gave the job to Ellie,
You're fine.
and I couldn't take it away from her.
That's
all right. All right. So we ended yesterday talking about chemical reactions, and we said that there's two types of chemical reactions. You have exergonic reactions, and you have endergonic reactions. And I wanted to start by doing a better job looking at these reactions. All right. So whenever you look at an endergonic or exergonic reaction, you're always going to be examining graphs or data tables like this. All right. With an exergonic reaction, you're going to have a high energy reactant being broken down into a low energy product. So I always think about comparing the two. In this case, you're going downhill, going from high energy down to low energy. As a result, the exergonic reaction is going to release energy. All right? So exergonic reactions release energy. During an exergonic reaction, what do you think you're doing? Are you making bonds or breaking bonds? You're breaking bonds, right? So what chemical reaction is being performed during an exergonic reaction? Hydrolysis. Good. Exergonic reactions are part of what type of pathway? Catabolic. Right? Exergonic reactions compose catabolic pathways. So if we went back to this picture right here, if this is a catabolic pathway, you would have multiple exergonic reactions that are linked together. And each of these reactions is going to be releasing energy. And that causes the entire catabolic pathway as a whole to then release energy. Does that make sense to all of you? Open the door, it's hot. The opposite of an exergonic reaction is an endergonic reaction, right? Which is doing the opposite. Endergonic reactions have low energy reactants being built into high energy products, right? Just like Mark has said before, you are constructing. And in order to build, in order to go uphill, you need to have an investment of energy. So endergonic reactions consume energy to build something. Endergonic reactions are part of what type of pathway? Anabolic. Good. Endergonic reactions are part of anabolic pathways. So if you were to again look at a pathway, right, this pathway is made up of multiple chemical reactions that are all consuming energy. They are all endergonic reactions as a whole, making this anabolic pathway. Do we all feel clear on that? So, if we look at the energy itself, right, in terms of what energy actually is, right? What is energy? We're talking about things consuming energy, things releasing energy. What is energy? Right? Energy is just simply defined as the capacity to cause change, or the ability to do work, or the ability to get something done. Right? That is how we define energy. And energy is going to come in two forms, right? Potential energy and kinetic energy. Kinetic energy is the energy of motion. We've talked a lot about kinetic energy when we talk about things like diffusion, right? And molecules moving from an area of high concentration to an area of low concentration, right? It's due to their kinetic energy, their energy associated with their movement. there's one type of kinetic energy that we have to talk about. It's heat or thermal energy. There's something important that you need to know about heat. Heat, biologically, is worthless. Heat cannot be used to do work, right? Heat is typically, a waste product that gets released, right? And heat cannot be used to get work done in the body. Is that clear to all of you? All right. The other type of energy is potential energy. Potential energy is the energy that something possesses because of either its structure or its location. So if you were to look at like a boulder on the top of a mountain, does that boulder have a lot of potential energy because of its structure or because of its location? Its location, right? If you look at a triglyceride, does that triglyceride have a lot of potential energy because of its structure or because of its location? Its structure. So something can have potential energy because of either where it's located, right? Maybe it's up high and it wants to go down, or because of its molecular structure. Right? We call this its chemical energy, right? Chemical energy is just a form of potential energy. So fats have a ton of chemical energy, right? And we can measure it. You learn that lipids have 9 calories per gram. Do you remember saying that? Calorie is a unit of what? What do you think a calorie is a unit of? Of energy, right? Calorie is a unit of energy. Somebody know what other unit we might use too besides calories? Joules. Right? Calories and joules are 2 different units of energy. They're 2 different units of chemical energy, right? Fats have 9 calories per gram. Remember how many carbs and proteins have per gram? 4 calories per gram. So lipids have more than double the amount of potential energy because of its structure. Now, we'll talk later on about laws of thermodynamics and the fact that energy is neither created nor destroyed. So if energy does not get created or destroyed, what does happen to it? It gets converted from one form to another. And we'll look at some examples of that. Here we see an example. Right? We see a diver jumping off of a diving board. All right? When he's on, or she, maybe it's a girl, I can't tell. Right? When she's on top of the diving board, first of all, when she's standing there, does she have potential or does she have kinetic energy? Potential. Because of her location or because of her structure? Because of her location. Good. When she jumps off of the diving board, her potential energy is now converted into what? Kinetic energy. And when she goes into the water, and now she's stagnant, still, again, her kinetic energy is converted back into potential energy. Right? And when she goes up the steps, potential energy is converted into kinetic energy. So the total energy is always constant, because energy does not get created or destroyed. But what I want you to see in this example is that energy is converted from one form to another form. Go ahead. You're good? Are you not confused anymore?
No, I confused myself by accident by overthinking it, so I'm good.
Okay. Joe, do you have a question?
No, I was just going to say, it reminded me of when I realized why Xbox Kinect was called Xbox Kinect. It utilized your kinetic energy to actually play games on it.
Okay. So it uses movement to power?
Yeah, but it doesn't work.
Okay. Separate conversation.
It's
Okay.
It's a big one.
All right. So on the board, you see a couple other examples of energy conversions. One that you see right here is the movement of energy up a food chain. And as energy moves up a food chain, it's going to start with the sun. It's going to go to a producer, to a primary consumer, to a secondary consumer, to a tertiary consumer. Things that we'll learn about later on in the year. But as energy is moving up a food chain, what is happening to a lot of that energy? It's being lost as heat, right? And what we'll learn later on, I'm sure a lot of you guys know this from environmental science or bio, is that as energy is moving up a food chain, it decreases by 90% at each rung in the ladder, right? So let's say you had, 100 units of energy here. Here you have 10, here you have 1, here you have 0.1, right? So if 10 is going from here to here, where's the other 90 going? As heat. Do we all see that? But one of the things that you should be able to recognize is even though the energy is decreasing by 90%, the total energy is staying constant, right? You have 100 here, and you have 100 here, right? Do we all see that? It's just that 90% of that energy that is usable is being lost as heat. But that total energy is remaining constant. Two of the best examples of energy conversions in nature are cell respiration and photosynthesis. Right? And you can see based upon this diagram that these two energy conversions are linked together. Photosynthesis takes solar energy, energy from the sun, and converts it into chemical energy, the energy found in chemical bonds. So photosynthesis is a beautiful example of an energy conversion. Solar energy converted into chemical energy. Cell respiration takes chemical energy, the energy found in sugars, and converts it into a different chemical energy, the energy stored in ATP. So both of these pathways in nature, both of these metabolic pathways are great examples of energy conversions taking place. Now, when energy is being converted, when energy is being used, we always look at something called free energy. And free energy is always designated by the letter G. Free energy is usable energy. It's the energy that can actually be used to perform work. Right? That is how you would define free energy. In other words, free energy is basically the total energy minus the amount that's lost as what? Heat. Because heat is not usable. So when we look at any type of energy conversion, we usually measure something called delta G. And delta G is the change in free energy. And the math here is extremely simple. There's a bunch of really complex equations that you can use. I like to use the most simple one. To measure delta G, you would take the free energy final minus the free energy initial. So you're taking the amount of energy in the end, and you're subtracting it. You're subtracting the amount of energy at the beginning. Now, once you measure the change in free energy, the important thing is that you need to determine if the answer is going to be a positive number or if it's going to be a negative number. Because whether or not that answer is positive or negative is going to tell you what type of chemical reaction is taking place. It's going to tell you whether that reaction is exergonic or endergonic. So if your delta G is a negative number, it tells you that your reaction is exergonic. If a reaction is exergonic, is it consuming energy or is it releasing energy? It's releasing energy. A chemical reaction that releases energy is referred to as being a spontaneous reaction. Meaning, it's not consuming energy. You're not investing energy. Instead, it's giving off energy. Right? So exergonic reactions with a negative delta G are referred to as being exergonic reactions. Or they are referred to as being spontaneous. If your delta G is positive, that tells you that your reaction is endergonic, meaning it's consuming energy, and you would call it non-spontaneous. So let's look at some examples. Let's go back to these diagrams, right? Now say you have your exergonic reaction. You have a high energy reactant. Let's give it an artificial number. Let's give the reactant 10 units of energy, right? And it's being broken down into a low energy product. We'll give it 2 units of energy, right? So delta G is going to be the free energy final minus the free energy initial, right? So you would do 2 minus 10, which gives you negative 8. Since delta G is negative, that means that this reaction is exergonic. It means that this reaction is giving off energy, or we would refer to it as being what? Spontaneous. Sorry. Spontaneous. Exergonic or spontaneous. Interchangeable. Spontaneous. Now you look at this one on the bottom here. You have the opposite. Low energy reactant being built into a high energy product. So now you have the final 10 minus the initial 2, and your delta G is going to be a positive 8. And a positive delta G means that this reaction is consuming energy. Right? It is an endergonic reaction if it has a positive delta G. We're all okay? Right, this is non-spontaneous because you have to put energy into the system. Now look at the girl jumping off the diving board, right? When she's at the top, did we say her energy is high or low? She's high, right? Might be 10 units of energy. She's got high potential energy. All right? She has a lot of what? Potential energy or kinetic energy when she's at the top? Potential because of her location. So again, we can give her a 10. When she jumps off the diving board, her potential energy is converted into kinetic energy back to potential energy. When she's in the water, is her potential energy higher or lower? It's lower, right? Again, because of her location. Because of her location, again, she has a lower potential energy. So if we looked at her potential energy final, 2, minus the initial 10, her delta G would be, again, a negative 8. So is her jumping off the diving board, would we call this reaction spontaneous or non-spontaneous? It's spontaneous, meaning Do I have to invest energy for her to fall from the diving board to the water? No, it would just happen. It's spontaneous, right? It doesn't need an energy input. Instead, I could probably release energy from this to do something. When these energy conversions take place, it's important that we always follow the laws of thermodynamics. Right? It's the study of energy transformations or energy conversions. Living systems, living organisms are open systems. I'll show you what that means, right? If you were to look at an insulated thermos, like this one, right? The goal of an insulated thermos is to be a closed system. Now, based upon just looking at a thermos, what do you think it means for the system to be closed? Yeah, there's no energy exchange with the outside environment. Does that make sense to you? And that is what would keep the liquid inside of here at whatever temperature that it was initially at. Because what is not being dissipated into the environment? Heat. Right? So the goal of a thermos, or anything that's insulated, is to be as close to a closed system as possible, where everything that's inside of this bottle is 100% contained, and nothing is being lost or exchanged with the outside environment. Does that make sense to you? Where if you have, like, my Starbucks cup, this is open. You got a hole right there, right? So this coffee is exchanging energy with the environment, right? What's being released into the environment? Heat. And what's happening to my coffee as a result? It's cooling down, right? Living organisms are not closed systems. Living organisms are open systems. And that is important to understand. What do we constantly give off to the environment? Heat. We're constantly losing heat to the environment, right? Now, this is a really difficult question. Super hard to understand. Since we are always losing energy to the environment, what do we constantly need to do? How? How do we get it? How do we get that? You eat. This is why we need to eat. Because eating is how we put energy into the body, right? So if we're always losing energy to the environment and we never put energy into our body, what would happen to all of our energy? If you lost energy without replacing it, what would happen to all of your energy stored in your body? It'd go away, right? And you'd die. Right? This is why organisms, especially warm-blooded organisms like ourselves, need a constant supply of food. We need food to maintain our body temperature, which is something that's weird. You don't think about it. You eat in order to keep your body at 98 degrees. And that's because we are constantly losing heat to the environment. We need to put energy continuously in because we're always losing energy to the environment. Does that make sense to all of you? That's a weird way because we don't think about eating to maintain body temperature. But it's true. You ever get a cold-blooded animal? Side note, like an alligator or a snake? A snake or an alligator could eat once every 3 months. Right? And that's because if they are to go into a cool environment, take an alligator and sink themselves into the cool mud, right? Their body temperature goes down. And when their body temperature goes down, what happens to the speed of all their chemical reactions? They slow down. And what are they not releasing into the environment then? Heat. So if they're not releasing any heat into the environment because they're not performing chemical reactions that give off heat as a waste product, they don't need to eat. You know, alligators and crocodiles and snakes, they were alive when the dinosaurs were here.
One of the things that we've discovered about dinosaurs, one of the things that made them go extinct, is dinosaurs were warm-blooded. They're not cold-blooded like reptiles today are. Another link between them and birds. So when a meteor hit the planet and food became scarce and the environment changed, the dinosaurs couldn't cope because they were warm-blooded. They need that constant supply of food because they were giving off so much heat to the environment. You take a snake or a crocodile or an alligator, they sunk themselves in the mud and they survived, right? And that's because they're not giving off heat to the environment as much as we are.
Crazy to think about. In either case, when these energy transformations are taking place, they need to obey the two laws of thermodynamics, right? Law number one, the conservation of energy. Like we've been saying all along, energy can be converted from one form to another, but it never gets created or it never gets destroyed, right? So the total amount of energy is staying the same. Now, the second law is super confusing, and you only need to know it superficially. When we give off heat, where does that heat go? Into the environment, right? And when it goes into the environment, it just keeps going. And it goes into outer space. Yeah. So all the heat that is dissipating from all the life on this planet is constantly being dissipated into the universe. And that's causing the universe to become more and more disordered as a result. Does that kind of make sense to you? We call this second law the law of entropy. And entropy is a fancy word for disorder. And the second law says that with every energy transformation that's taking place, the universe as a whole is getting more and more disordered. And it's all because of the what that we're constantly dissipating into the environment. The heat, right? It's all because of the heat that we are dissipating into the environment. Now, does the law of entropy have anything to do with the amount of order that is on Earth? No. Does it have anything to do with the amount of order in your body or in your cells? No. It's dealing with the amount of order in the universe, in outer space. So with every energy conversion, with every chemical reaction taking place in our bodies, and as all living organisms are dissipating heat into the environment, it is the universe as a whole which is becoming more and more disordered. Right? That is the key. It's not about what's happening in your body. It's not about what's happening on the planet. Because you can create order in your body. You can create order on the planet, right? But as you're doing so in outer space, in the universe, it's becoming more and more disordered as a result. Make sense? This is the perfect place to end it today. All right. There's a good little video on the PowerPoint if you want to check it out. But